In this lesson, we'll look at how to set up an internal flow analysis on this pipe using the SolidWorks Flow Simulation Wizard. By internal flow analysis, I generally mean that the fluid will enter the model through one or more inlets, such as this opening here, and exit the model through one or more outlets, in this case these two openings. There are a couple of other special types of internal flows, but for the most part, when thinking of internal flow problems, you can generally think of them in this way. Before I get started, let's take a look at what we have going on with the part file. This is a multi-body pipe part. It consists of a shelled sweep, which makes up the main pipe body, and three lid bodies which close the inlets and outlets of the pipe. These lids were created using the Create Lids command. In order for Flow to properly run an internal flow analysis, all of the openings on the model must be covered using a lid feature. If this were an external analysis, such as the flow around an airfoil, for instance, the lids would not be required. But to conduct an internal study, Flow asks you to first cover all of the openings using lid features before setting up the simulation. To begin, I'll launch the Flow Simulation Wizard from the Flow Simulation drop-down under Project and click the Wizard icon. The wizard makes it easy to set up the basic specifications required to conduct a flow study. The first thing I'll do here is create a new configuration for the flow simulation. I always like to create a new configuration for each flow study that I perform to help keep my files and results organized. I'll call this Internal Flow Study 1. SolidWorks will automatically create and activate the new Internal Flow Study 1 configuration, and all of the data for the flow study will be stored in a new Internal Flow Study 1 folder, which will be located in the same directory on your hard drive as the part file. I'll click Next to continue with the wizard. Now I can select the units for the study. You can choose from any of the predefined standards in this list, or you can create your own new unit system using the Create New checkbox. For this example, I'll choose the standard SI units, meters, kilograms, and seconds. With the unit set, I'll click Next. The next step in the wizard is asking us to specify the analysis type. As I mentioned at the beginning of this lesson, we'll be running an internal analysis on this pipe. I'll also uncheck the Exclude Cavities Without Flow Conditions checkbox. Since there is only a single internal space within this model, we want this option cleared. If there's more than one internal cavity or space in the model, such as a separate chamber or compartment, then we would want to activate this option, as it would prevent SolidWorks Flow Simulation from meshing and solving for those extra areas that don't have boundary conditions. I'll leave the rest of the options here at the defaults and click Next. In this window, we'll define the fluids to be used in the analysis. For this example, I'll use liquid water. I'll browse for it, and when I double-click on it, you can see it's automatically added to the project fluids list. The rest of the default settings will work well here, but I'd like to point out the flow characteristics here at the bottom. This shows what type of flow the fluid will encounter, in this case, laminar and turbulent. Again, I'll click Next. Now we'll specify the wall conditions. If you've ever taken a thermodynamics course, you'll remember that an adiabatic process is a process in which absolutely no heat can be transferred to or from the working fluid. Basically, using an adiabatic wall condition assumes that the walls are perfectly insulated. Since this analysis doesn't involve any heat transfer, this is the condition we want to choose. If there was heat transfer involved, we would select a different option. The roughness value that you set here is used in the calculation of the velocity profile within the boundary layer of the flow. If you don't know the exact roughness value for the inside of the pipe, I always recommend using 0. A roughness value of 0 means that SolidWorks will assume that the walls are perfectly smooth. In the next window, we'll set the initial and ambient conditions for the analysis, such as the pressure and temperature, and a few other properties. I'll leave all the initial conditions at the defaults and click Next. Here we determine the mesh and results resolution. I'll set the result resolution slider to 3, This slider controls not only the resolution of the mesh, but also other important parameters of the solver, such as the convergence criteria. The result resolution requires you to balance between the desired precision of your results and the computation time needed to complete the study. The higher the resolution here, the finer the mesh. This also means there will be more mesh elements created, which in turn will require more processing power from your computer, and the study will take longer to run. However, higher resolution narrows the convergence criteria, making the number of iterations required to achieve convergence criteria more accurate. In general, choosing 8 for the resolution will result in the finest mesh, longest computation time, and more precise results. Choosing 1 will result in the coarsest mesh, shortest computation time, and less precise results. For this example, 3 will work just fine. In certain situations where you have really small features, manually entering values for the minimum gap size and minimum wall thickness is important. That way you can be sure that any small features are not ignored during meshing. Since this part has a fairly uniform diameter throughout, we can skip these options. This completes the wizard, so I can go ahead and click Finish, and the study setup is complete. I'll click on the Flow Simulation tab in the Feature Manager tree to see what we have so far. If at any time you decide to change any of the input data that was entered when setting up this analysis, you can do so by right-clicking on the Input Data folder in the Flow Simulation Analysis tree and selecting the option from the drop-down menu.